Do you have big problems that only big parts can solve? And maybe your tools are just a bit undersized for the task at hand? Well, I've got the same problem, and this is the video for you. In case you missed part 1, I'm trying to build a robot arm that can do amazing camera moves, and I'm doing it all in my home shop. In the last video, I built the wrist, which contains axis 5 and 6. So now we need a way to support that wrist. So we're building the frame for the forearm. And well, it presents some pretty big problems. But we'll get to those in a little bit. For now, we can basically think of the forearm as a big box frame structure. Now, is this the best shape for the forearm? No, it's not. A cylinder would be much more resistant to the bending load. But we need to be able to actually manufacture these parts, so that means we're building it out of plates. So we'll have to rely on press fits, bolts, and a few tricks I'll explain in the future to hopefully give us all the strength and stiffness we need. So we'll get warmed up with the smallest plate, and work our way up from there. It's a fairly basic part, but the outside dimensions are pretty important for maintaining the proper spacing of our box structure. The large pocket in the center just helps keep the weight down, but hopefully leaves it stiff enough to do the job. And I nailed the outside dimensions, and was well on my way to my first finished part. All I had to do was flip it around and face off the other side and I'd be done. This was all going really smoothly, and I was feeling good about... Aw, crap. It's not even close to flat. I think I can save it though. I haven't machined the side plate, so I just need to machine the mating feature to match whatever thickness I end up with. After fly cutting on the manual mill, the part was even worse. So it was on over to the lathe. The old gal has never let me down. Seriously? Okay, we're done here. So what happened? Had my trusty superglue method finally failed me? And lathe, how did lathe let me down? No, this was a problem that actual machinists like to call a complete and utter lack of experience. Superglue mill and lathe hadn't let me down. I had failed them by not getting my order of operations right. I was trying to face the plate down to height after having already removed a large amount of material in the form of this pocket. So this didn't exactly leave me with a lot of surface area for the glue to hold. And likewise in the mill, the clamping forces had likely caused the part to banana a bit. I thought the forejaw on the lathe would alleviate this problem by spreading the clamping force. It didn't. So I remade the part, this time facing the opposite side first, then flipping the part around to machine all the rest of the features. But the seeds of doubt had been planted. Was I really up for this challenge? And then the part finished, and it's pretty darn flat. So I'm gonna say we're good to go. But wait, this video is about large parts, and so far, I'm just remaking parts that could only be described as medium at best. Trust me, I'm not happy about it either. So let's step it up a bit size-wise. Or at least thickness-wise. I'm calling this part the base plate. It has a pocket machined in the exact center, which will connect the forearm to a shaft, connecting the entire assembly to the elbow joints. And that means there's going to be a heck of a lot of stress placed on this plate, so it needs to be fairly beefy. But as always, weight is the enemy, so I'm removing as much material as I think I can get away with. To help with this, I did some simulating for this part. But to be honest, I can only wrap my mind around the most basic simulations. And robots move in complex ways. So this is a case of guess and pray engineering. Now, one thing that I don't think is often clear from these kinds of videos is just how long these parts take to make. Well, this base plate took a little under 6 hours of actual machining time. And when machining for a long time, especially cutting dry like I am, parts tend to get hot, really hot. And we all know things expand when they get hot, so it's important to let the part cool down before cutting any of the critical dimensions. Plus, my machine is not an industrial machine, so I give it a lot of breaks to cool the spindle down. So that's 6 hours, plus a bunch of wait time. I'll lathe the shaft up later and custom fit it to the bore. so I just did my best to hit the dimension here. The critical locating features for both of the plates were machined in the manual mill, since I don't have the vertical clearance on the CNC. They had to be machined this way because of the sharp 90-degree inside corners. This meant carefully finding the center of each part and removing an equal amount of material from each side. And then it was time to drill and tap holes. Center drill, follow up with the tapping drill, tap, then repeat 48 times. Yes, you heard that right. There are 48 threaded holes between these two parts. And this took a long time. Like all the manual machining on these parts took almost 5 hours. I need a better solution. But now I have 2 parts that I can use to test my fits as I machine up the 2 side plates. Now these pieces are big. The biggest pieces I've ever machined by a lot. And the actual subject of this video. So thanks for sticking with me this far. So here's the problem. My router isn't big enough to machine the plates all in one go. They will physically fit within the machine, but it can't actually travel the full distance required to completely machine the part in one go. So what's the big deal? Just move the part and machine it in 2 setups. Well, CNC machining is kind of like following a map. You won't know where you're going until you've figured out where you are. In machining, this is done by setting an origin for each setup. The machine uses this origin as a reference for all the toolpaths in this setup, so it's pretty important. And these are the most critical features on this part, and they're too far away from each other to machine in one go. But it's critical that we get the distance between them right. So how do we do this accurately? Well, one option would be to machine our origin at the halfway point between these 2 critical features, a feature that could be accessed in both setups. But to be honest, I don't know if I trust myself or my machine enough to do this accurately. Plus, I need to machine the outside edges of the part, and I need to ensure the part doesn't rotate when I change the setup. So ideally, I'd have a solid reference edge to ensure alignment with the axes of the machine. All these issues were piling up, and I had really started to stress out about making this part when it hit me. I could just outsource this problem. It turns out that getting flat sheets cut on a water jet is surprisingly affordable, like maybe 20 to 25% more expensive than the raw aluminum. So I designed up some blanks and sent the design off. These blanks would have a finished outside profile, so that takes care of the reference edge. In addition, I included locating features for the 2 setups. So now my origin would be taken care of. Did I say 2 setups? Yeah, actually it's 4 setups, since I have to machine both sides of the part. So yeah, this is kinda complicated. So my blanks arrived and it was time to get started. To begin, I machined a straight edge into the spoil board to locate the part on the y-axis. Then dialed in the first reference to establish my origin. And away I went. The first critical feature was this pocket, which locks in the base plate. I used the previously machined part to double check my fit. After that was done, I remachined my reference, but I'll talk more about that later. Then it was time to flip the part around and get started on setup number 2. Here, the important features are the pocket and bore that locates the gearbox for axis 5. Sneaking up on those dimensions, and lots of test fits later, and the gearbox fit was looking good. So now it was time to flip the part over and start the most extreme weight loss plan possible. Material removal is the name of the game here. And once again, I think it would be good to talk about just how long all this took. 10 hours. That's the total machining time per side plate, plus breaks and cooling time. So yeah, patience is really important. And while this is humming along, I thought we could take a moment to talk about stress, and not the kind that comes from machining a complicated part. You might have noticed that I'm doing a lot of heavy cutting on only one side of this part, and the experienced among you might already be shaking your heads. So let me explain why. Most metal stock has some amount of internal stress stored in it, and when you machine only one side of it, especially removing as much material as I am, then you're just begging for that part to warp as that stress releases unevenly. So what was my master plan to deal with that? Well, some of you may have heard about a magical material called Mic 6 aluminum. Mic 6 is a cast aluminum and is very flat and dimensionally stable. It has very low internal stress, and bonus, it's super easy to machine. Truly, it's a wonder material. I should just machine the whole robot out of this stuff. Or maybe we instead call this whole situation a lesson in not getting too clever for one's own good. I mean, who would have guessed that Mic 6's tensile strength would be less than half that of the 6061 I've been using up until this point? Definitely not this guy when he ordered those blanks and then spent 4 days machining them. So yeah, that happened. Pretty much all my simulation and testing has been on 6061, so hopefully this won't cause major problems in the future. And I really hope that's not foreshadowing. So let's get back to something that actually went well, and that was thread milling. I told you I was tired of drilling and tapping, and wow, what a relief it was to watch my machine cut so many threads. If you're unfamiliar, thread milling allows you to cut a thread on a CNC machine without having to use a tap. And this means that you can even do it on a machine as wobbly as mine. So after all the holes and threads were done, I could finally call this part finished, at least the CNC portion. So it was time to move on to the second plate, which was pretty much exactly like the first one, but cursed. So first off, this bore that locates the axle we made in part 1. This went smoothly, and then my machine crashed. Why? Ghosts? In any case, there was a glitch that made me reboot. But little did I know that this had also caused my origin to shift. So as I started on the holes that surrounded the bore, I noticed something wasn't looking quite right. As in, the hole pattern wasn't centered on the bore. So I had to rotate the pattern and re-drill, after recentering the machine on the origin point, of course. Luckily, the bad holes won't be visible after assembly, but my pride sure took a hit on that one. Then, when I went to do the pocket that secures the base plate, I nailed my fit. Well, everything except the depth of the pocket, that was. I was just slightly short of tolerance there. An insignificant amount. Minuscule, even. But my wounded pride wanted to nail it. So I took one more pass, and I think you know where this is going. I swear I had double-checked my tool pass for clearance on the walls of the pocket. But as the machine made its final pass, the unmistakable sound of end mill on aluminum told otherwise. And in seconds, my perfect fit was ruined. You are now witnessing the acts of a desperate man. Remember, I'd invested 6 hours in the base plate, and many more in the side plate, and I didn't want to order another blank. So I took option C and gobbed a bunch of JB Weld epoxy onto my base plate, and then remilled the locating features into the epoxy. Yeah, I know. But this is a prototype. I was kinda joking about that whole guess and pray engineering thing, but for these parts it's kinda turning out to be true. So after hopefully but probably not saving that fit, I finished the rest of the machining for the side plate, and everything went smoothly, thankfully. And once again, I was grateful for those thread milling ops, because there were a bunch more manual holes that needed drilling and tapping. Yay. I don't know why this annoys me so much. There are lots of tedious tasks in machining, but none of them instill nearly as much dread as drilling and tapping. So there you go. And you can tell how much I'm not into this by my really sketchy setup. Oh, and my very precise way of repositioning the part so I can get all the holes drilled. But I'm gonna call it good enough. And wow, what a marathon that was. But we got there in the end. And that extreme weight loss program worked wonders. So how would I rate my whole plan? Honestly, not that great. And I'm not just talking about that whole pick the wrong material thing. The reference edge worked fine, but remember those 2 locating features? You know, the whole reason we got the blank made in the first place. Yeah, they didn't work so great. Turns out the water jet leaves kind of a rough surface finish, which is not ideal for using it to establish an origin. So many lessons learned, and I'll probably try something else for the next round of large parts. Or maybe I won't. I really haven't gotten that far yet. In any case, I think we all deserve a well-earned reward in the form of a sexy parts montage. Thanks so much for watching. Please like, comment, subscribe, and ring the bell, and I'll see you on the next one. And if you missed part 1, watch it here.